Welcome back to chapter 18. So we had just discussed various directing effects in section 18.7, and I basically lumped everything that is discussed in the subsequent 3 sections in there as well. I had introduced this table. I had encouraged you to look carefully and closely at structures. It becomes really important that you have a good command on placing non-bonding electron pairs and putting good formal charges, and that when we are looking at an aromatic ring, that the first position, the atom that is connected next to it, plays a pivotal role as to determining so in this position here, what atom it is, whether it's a free electron pair, whether it is a multiple bond, so on and so forth. So I'm going to go through the next 3 sections rather quickly because they're basically review. I hope that the previous section on 18.7, that focus has helped you understand some of the material. So let's look at this again. We had also discussed ortho-para directing effects and meta-directing effects. We discussed activating and deactivating groups and how all of this ties in. We had also looked at these diagrams where whenever we have an activator, something that is capable of putting electron density into the aromatic ring and thus increasing nucleophilicity, will basically activate in the ortho. There are 2 ortho positions and the para position. And so I've redrawn that here with electron donating group. And then we have deactivators that will take out electron density. And in those cases, we will see a delta negative charge in the meta position. So that will then still be able to act as a nucleophile in an aromatic substitution reaction. Moving on. So I had mentioned before, it's really important that you are able to draw a detailed structure. So it may say NO2, and you need to immediately think that, oh yeah, here's an atom. There's a multiple bond, double bond to oxygen, there's a positive charge, and it will take out electron density. So thus it's a deactivating group. It's going to slow down the reaction, and it will be meta-directing. As previously, we can now do more electronic analysis through resonance forms. We had talked about 2 methods in which this electronic effect can be expressed. There's the inductive effect that is weak, more weak, and then there is the resonance effect that is stronger. Because nitrogen is more electronegative than carbon, there is an inductive effect. And in addition to that, because of this multiple bond, we can now formulate all these resonance structures. I would encourage you to pause the video here. Maybe start out with just the structure here and then try to formulate all the other structures and practice your curved arrow formalism in this. Moving on, here's some information. Nitrobenzene undergoes nitration 10,000 times slower than benzene, which is just another part or evidence that this nitro group is deactivating because of how it takes out electron density. And here we can see that the ortho and para position are really small amounts in the mixture, and that the meta substitution product will be the main product, the major product. On the next slide, here we see an analysis as we had done before with activating groups. Once the nitro group attacks the electrophile, remember the aromatic ring is your nucleophile, and we had discussed how potent electrophiles are formed under various conditions. We then go through the system of ortho, meta, and para attack and analyze the structures. And then we see that it's really a very bad idea to have an ortho and a para attack, because as we're analyzing this here, remember that the nitrogen of the nitro group has actually a positive charge, and to have 2 adjacent positive charges is really a very bad idea. So that is really, those are resonance forms that are not helpful for stabilizing the various intermediates of the sigma complexes as they are described here. And as we did before, we can look at an energy diagram. We see that, yeah, that positive charge next to the nitro group is really bad. And look how high this is in the energy, right? So here's your energy on this axis. The ortho attack, it looks really bad. The para attack looks really bad. And that the most stable position is for the meta substitution product. So as we're looking at this, again, all electron donating groups are ortho-para directing, all electron withdrawing groups are meta-directors, except the halogens. So I referred to them before as Jekyll and Hyde. So halogens have a kind of a mixed effect. Halogens will withdraw electron density by induction, which is deactivating. Induction means the effect is only felt through the single bonds. This is a minor effect. It is a smaller effect compared to resonance. But remember, whenever we're looking at a carbon halide bond, and you learned a lot about this in Orgo 1, especially regarding substitution reactions, the electron density is going to be drawn towards the halogen. So this is delta plus on the carbon and delta minus on the halogen. This is an incomplete structure. We have other things attached here. So this is just to focus in on that bond. However, we also know that halogens have the electron pairs. So 1, 2, 3, 4, 5, 6, 3 electron pairs. Looks a little bit crooked, but 1, 2, 3, 4, 5, 6, 3 electron pairs. And they are now actually able to donate electron density through resonance, and that is through making a double bond, pi bonds. That is the key aspect to remember here. So here we now see halogens withdraw the electrons by induction, inductive effect, but they donate, so withdraw, induction, donate through a much stronger effect, which is resonance. So once we actually have the sigma complex can help stabilize, we can also start out with a neutral molecule and just go through the mechanism, and then we see that whenever we have an atom with electron density, it is able to put that negative charge in the ortho position as shown here, the para position as shown here, and again the other ortho position. Thus they are ortho-para directing. And we can again make a very detailed analysis. I encourage you to pause the video here, jot down the structures, and do your own analysis. Again, we're looking at a halogenated benzene, so chlorobromobenzene, reacting with a potent electrophile, E+. In this case, it would be NO2+. And what would the resulting sigma structures look like, and then look at the quality, the stability of these intermediates, of these sigma complexes. So as we're looking at this, we see ortho and para actually has 4 possible resonance forms compared to only 3 resonance forms for the meta attack. And the reason that there are 4 structures here is because the chlorine position is going to be perfectly aligned to now be integrated into forming another resonance form. There are different ways of drawing this. We can also get more quickly to the structure. But basically, for chlorine to have an involvement in these intermediate formations, it has to be the ortho positions or the para position. Otherwise, we cannot put the electron density in there. So 4 resonance forms, more stable compared to only 3 resonance forms that we are seeing here. On this slide, we're now going to go through some of the examples. I encourage you to jot down the structures, write in your own words what it means to have these. So here we're starting out with strong activators. They are ortho-para directing. what these all have in common is an electron pair on the atom that is directly connected to the benzene ring. That's an OH group, O minus, an NH2 or NHR or NR2. Then we have moderate activators. They also have in common that the first atom connected has electron pairs available, like this oxygen, nitrogen, nitrogen, and then here an alkoxy group. The moderate activators are not as strong as the group that is shown up here, because if we're thinking about it, a carbon is going to be more electronegative than, let's say, a hydrogen. So that would be up here. It's a slight effect. There's an even stronger electron withdrawing effect whenever we have a carbonyl group attached, and those are the other three groups, other three functionalities. So the carbonyl group here, remember, there's a multiple bond, and this electron density can be sucked into the carbonyl group. So that is going to have a modulating effect, and therefore they're not as strong activators as the group shown above. Here we see weak activators. These are all our R groups shown here, whether it's a T-butyl, isopropyl, ethyl, methyl. These are only weakly activating because here we only have an inductive effect. There are no double bonds involved. There's no electron pair. And then as we go on, we now see strong deactivators. I wish they had switched this direction. Strong deactivators. Remember the nitro group. You're now aware of the bonding pattern. There's a positive charge on the nitrogen. Same as here, whether this is an ammonium substituent, meaning NH3 plus, it's a positive charge, or these could be alkyl groups. That positive charge, though, is the key for these being deactivators. And then here we have a carbon that's connected to 3 halogens, so there's a strong delta positive charge because the halogens are inductively withdrawing electron density. So delta plus, full positive charge, strong deactivators. And then, as I mentioned before and I had outlined in the table, whenever we have a multiple bond, whether that is a carbonyl group in a ketone, carbonyl group in an aldehyde, carbonyl group in an ester, carbonyl group in a carboxylic acid, carbonyl group in an amide, and then carbonyl, 2 actually double bonds in the sulfonyl group, and then here we have the nitrile group, right? So this might just show as CN, and then, but you need to know, ding, 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 there are 3 bonds here, and you need to remember the bonding patterns. That's really important to come up with the best solution. And then last but not least, we have our weak deactivators. So those are all the halides, chloro, bromo, and iodo, but they have the electron density, and they are deactivating groups through inductive effect, but they are also orthoparadirectors because they can lend an electron pair to stabilize some of the intermediates or to increase the electron density in the ortho and para position. Okay, and you have this also in your table 18.1 outlined in your textbook, and you can practice with Skill Builder 18.1. And let me just switch over real quick. There's also Skill Builder 18.2. And we can have a mono, di, or multi-substituted benzene ring, and then apply all the aspects that now are based strongly on the electronic movement, induction and resonance possibilities, and you need to basically look at different examples to then make an assessment and practice this. Okay, so we're gonna end or take a break right here.